Okay, the other structural isomer, so the linkage isomer is one type of structural isomer. The other type is a coordination sphere isomer. So we talked about the coordination sphere, that's what's inside the brackets on one of these complexes. And you can imagine having isomers with the same overall formula but different arrangements. So let's see here. We have a hexaaqua chromium compound with 3 chlorines outside of the coordination sphere. That's one type of way we can arrange 6 waters and 3 chlorines around this complex. The other way is to do 5 waters bonded to the central chromium, 1 chlorine bonded, and then 2 chlorines and 1 water, or so on and so forth, 4 water with 2 chlorine, 1 chlorine, and then 2 water outside of the coordination sphere. So again, overall, that whole formula is the same for each of those complexes, but what is bonded to the coordination sphere, which is what is bonded to the central metal atom, is different. So coordination sphere isomers differ in which species act as ligands, those are inside the coordination sphere, and which are outside the coordination sphere. Okay. How's that one? That one okay? That type of isomer? Okay. Those 2 types you don't see all that much in organic chemistry. Stereoisomers you do see a lot more frequently. So stereoisomers, like I mentioned before, have the same bonds but different spatial arrangements. So great examples of this are the cis and trans isomers of the platinum complex, that is this, so platinum, NH3 Cl2. Does anyone know what this is used for? If I say cisplatin, does that help? What's cisplatin used for? No? Anyone? I'm glad you don't know, actually. It's a cancer treatment. So cisplatin, which is this stereoisomer, 2 chlorines on one side, 2 ammonia on the other, central platinum atom. This is a chemotherapeutic agent. If you take one of the ammonia and one of the chlorine and switch their position, and now we have, this is a square planar complex, right? And now we have the chlorines across from each other, and the ammonia across from each other, transplatin. This is not a chemotherapeutic agent. Does not work. Okay? So just this simple rearrangement of atoms this way, spatial rearrangement, can make a therapeutic work or not work. Naproxen is another type of isomer like this. Naproxen is a leave, and one of the isomers works and the other one doesn't for pain and whatnot. If you've ever gone shopping for pain medication, you notice that a leave is more expensive than the others usually, and that's because we're separating out cis and trans isomers, and it takes a lot more manufacturing in order to do that. Okay, so cis and trans, we've been using those terms. Cis isomer, atoms of a type are on the same side. Trans, they're on the opposite side. And the other thing to note here, we see this typically in square planar complexes. Okay. So this is a good example. If you have, in complexes that have 4 bonds to the central metal atom, we're ignoring the lone pair electrons. We have our options for geometry of, what do I see up here? Options of geometry of square planar or tetrahedral. And the tetrahedral arrangement, if you have this same collection of atoms, but it's arranged tetrahedrally, there's no isomers. okay, because the tetrahedral geometry allows for rotation that doesn't differentiate between these types of arrangements. Y'all don't have model kits, do you? You get those probably next, if you're in organic. I should have brought the models in again, but sometimes tetrahedral is really hard to see. There's a central metal atom, 3 bonds, but they're sort of like a tripod. So you can rotate that in various ways to sort of eliminate any sort of stereoisomer possibility. So you don't see stereoisomers with tetrahedral compounds, is what I'm trying to say. So the other types of stereoisomers, a little bit more on this. We have optical isomers. So these are mirror images of one another, but they don't superimpose. So your hands are stereoisomers. They are mirror images of each other. But if you try to overlap them perfectly, you can't do it. This doesn't match because now that's a mirror image. So that's an optical isomer. Mirror images that don't superimpose. And those molecules are what we call chiral, or optically active. And they have certain properties where they interact with light in certain ways. And you'll see this a lot more, again, if you're taking organic. You'll see dextrorotatory, which means that a certain type of molecule will rotate light, which way is this, to the right, and then levorotatory rotates it to the left. Okay. Thinking about rotating light is kind of fun. You don't need to get into that too much, but I do want to point out these enantiomers with this cobalt complex. So we can imagine that these nitrogens and then this sort of ribbon represents the ethylene diamine ligand. Okay? And these complexes are optical isomers. They're enantiomers. So this dotted line is going to represent a mirror. If you look at the arrangement, again, you have to think sort of 3D and 3-dimension. So this atom is sort of back into the plane of the board. This one's perpendicular parallel with the plane. This is coming out towards us, going back. And so when we have these ethylene diamine ligands, which are bonding in those 2 locations, and we have 3 of them arranged in a certain way, we're able to produce an optical isomer. So if you were to have these 2 molecules and try to superimpose them, you wouldn't be able to do it, okay? You have these 2 mirror images. There's a couple of good websites for sort of viewing 3-dimensional things like this. Maybe I'll try to find a link for you all and put that on Carmen if you're struggling with that sort of picturing these in 3 dimensions, especially with a bidentate ligand is tricky. So, but again, if you see an ethylene diamine ligand or something that's bidentate, think about the possibility of an optical isomer. Okay. So there is a really nice flow chart, I believe this is from your book, that walks you through determining whether or what type of isomers are present. So you can walk through this and say, do the molecules have the same types of atoms? If they don't, then there's no chance that they're isomers. Okay? If they do have the same types of atoms, then yes, we could possibly have an isomer. If they have the same bonds, meaning the atoms are linked in the same way, no changes with the central metal atom, then we have stereoisomers. If those atoms aren't linked in the same way, then we have structural isomers. And those are the ones we talk about. Those ones, I believe, at least in terms of how I feel about it, are a little bit easier to recognize. There we have the linkage isomers, which only shows up with nitrite and thiocyanate ions. Okay, so if you don't see those, probably don't have a linkage isomer. And then the coordination sphere isomers, these are the ones where the ligands inside the coordination sphere and those ions outside of the sphere can be rearranged, but overall have the same formula. And then the stereoisomers. These are where it's a little bit trickier. We have the geometrical isomers and the optical isomers. So the geometrical isomers, these are like your cis and trans complexes, and then the optical isomers are the ones that have mirror images that are not superimposable. So I would, if you're going to just sort of focus on a couple of things here, this chart is great, but also I think identifying the difference between geometrical and optical isomers can be a little tricky. Okay, so take a look at that. All right? Questions on that? Here's a very blurry picture. We can do this example. Which molecule does not have a geometric isomer? So again, geometric, cis and trans. So, does anyone know the answer? A, that's correct. So A is tetrahedral. Okay. A is tetrahedral. There's, so even if there were two yellow atoms and two green atoms, there's no way of creating a geometric isomer with this. What about B? So B is like cisplatin, right? So you can move one of the yellow, so you could have something like this. Here's our green, here's our green, and then yellow, which is orange, and that, like that. So that would be the trans. And then I think with the octahedral complexes, it's a little bit harder to see. But these do have geometric isomers. So again, we'll take our central metal atom for C. 1, 2, 3, 4, 5, 6. If we have this as the trans isomer, because the yellow are across from each other, across the central metal atom, and then instead we move yellow here, and then the rest green. Now they're next to each other, and you can think about them being on the same plane. That's different. Okay. So this would be the cis. And then when you get 3, again, central metal, 1, 2, 3, 4, 5, 6. We would have to take one of the yellows and move it into the plane portion. So we're going to have 1, 2, 3. And then 1, 2, 3. Okay? The naming convention will be a little bit funky there, but it does have a nice